Now we are ready to formally state and prove the Maa-ler's compactness criterion. We write x sub d to be the quotient of SLDR by SLDZ, which is the homogeneous space of right cosets of SLDZ in SLDR. And Maa-ler's criterion states that a set K contained in x sub d has compact closure. Remember, the topology here is the quotient topology of SLDR, and SLDR has a subspace topology inherited from the Euclidean space. As compact closure if and only if there is an S greater than 0 with the property that the intersection of any lattice lambda in K only has a trivial intersection with BS0, the ball centered at 0 at the origin with radius S. So this is true. So this is true for all lambda in K. And that is the Maa-ler's compactness criterion. Let me make a remark here that this property, the property that there exists a small ball at the origin such that any lattice in this set K has only trivial intersection with a small ball. This property is called the uniform discreteness property. Because we know that every lattice is already discrete, and when every lattice in some set is kind of uniformly bounded away from 0, we should call it uniformly discrete. Now let's start proving this theorem. Usually, if there are two directions to prove in a theorem, one direction is usually much easier than the other. So in this situation, can you see which direction is much easier than the other? I will let you think about it for a while. It turns out it will be easier to prove that if you start with a set with compact closure, then it has the uniform discreteness property. So this direction is easier to prove. This is basically because, well, this is just my personal feeling, because the compactness is a kind of a more abstract notion. There are much information in this compactness. But this uniform discreteness property is kind of more intuitive, more concrete. So it might look easier to start with a more abstract notion to prove a more concrete notion. But I told you this is just my personal feeling. It may not be universally true. Okay, now suppose K as a subset of XD has compact closure. But this uniform discreteness property is failed. Namely, for every positive number S, you can always find some lambda in K such that this intersection is non-trivial. And let's just take a special case. Let's take some special S. But for every n greater or equal to 1, there is some lambda n in K with lambda sub n intersection the ball center at 0 with radius 1 over n, non-trivial. And by the pre-compactness of K, there exists some lambda in X sub D with lambda n converges to lambda. So I should explain let me explain what's happening in here. What's happening here is that when you start with a pre-compact subset, you get the pre-sequential compactness. So this property implies that this subset K is also pre-sequential compact, which means there's a subsequence of lambda sub n that converges to lambda. And by passing to the subsequence, you may assume that lambda n itself converges to lambda. And this lambda, this is just pre-compactness. So this lambda may no longer be in K, but it should always be in XD. So I should add here that by passing to a subsequence and with the abuse of notation, we may assume that lambda sub n converges to lambda. And now why the pre-compactness implies the pre-sequential compactness? This part follows from the fact that X sub D, which is the quotient of S of dr by S of dz, is Hausdorff. And why is it Hausdorff? This is because S of dz is closed in S of dr. So if you have a topological group and a closed subgroup, you can prove that the quotient is always Hausdorff. The proof for this fact is not hard. You can simply Google it online, or you can find it, the proposition 3, on the page 232 of the book Linear Analysis and Representation Theory by Stephen Gao. This is a very good book, very readable book. you may want to take a look at this proposition in that book. Proposition 3 in page 232. And I should also clarify the meaning of the convergence of lattices. By that I mean there exists a sequence of bases of lambda sub n's that converge to some basis of lambda. I will write it down more explicitly below. Remember by the facts we mentioned in the previous video. So by definition of lattices, by the 1-1 correspondence between xd, which is this quotient, and space of unimodular lattices in Rd, we can write lambda sub n equal to g sub n inverse dot zd, and lambda equal to g inverse dot zd. And we can choose g sub n. Remember, g sub n is only unique up to a left multiplication. Because remember, in our first video we were talking about this correspondence. We're taking the right cosets, so every element here is not uniquely defined. There will be right cosets, and thus there will be basis. Let's call it b sub j with a superscript n denoted gn inverse dot ej. Remember, this is a standard basis in Rn. 0, 0, 0, 1, 0, 0, 0, where j ranges from 1 to d of lambda sub n, which converges to a basis. Let's call it b sub j equal to g inverse ej, where j ranges from 1 to d of lambda. And now let's draw a picture. Let's just consider the dimension 2 case. Suppose this is a g inverse dot e1, and this is g inverse dot e2, and you have a sequence of lattices converging to this guy. So say this is gn inverse dot e1, gn inverse dot e2, and there's the convergence. Because lambda itself is fixed, the fixed lattice in x sub d. This means when n is sufficiently large, those lattices have to be bounded away from 0. If this is 0, then as n becomes very large, those lattices have to be bounded away from 0 because their basis vectors are getting very close to the basis vectors of lambda. But lambda itself is bounded away from 0. So no elements in those sequences can be close to 0. So this implies lambda sub n cannot contain arbitrarily small elements in Rd, which is a contradiction to our assumption that lambda n intersection the small balls centered at 0 with radius 1 over n is now empty for all n. This is the end of the proof of the first part.